Hey guys, Mr. Goya coming at you here. Hey, today we'd like to look at type 3 trajectories. Hey, these are pretty challenging problems. Mathematically, they involve a little bit of hard mathematics. At least, you might think it's kind of challenging. It's really not too bad once you get into it, but you have to be careful. Make sure you have a calculator with you here. It's in degrees, not radians. Hey, we're going to do page 8. We're going to start with page 8. And let me kind of, again, do a couple problems here with you here. Now, the other day on page, I think it was 6, we did kind of this Nick punting a football problem. Well, let me make it a little bit more realistic, and let's turn it really into a type 3 projectile. So let's redo the first problem that we did. That would be page 6, but let's make it a little bit more realistic. Nick punts a football from above the ground, so his kind of foot really is above the ground. We're going to call this in our reference point, so we're going to call this 0 meters. He kicks it with an initial velocity of 25. That's the same velocity we had before. That's called our VI. Okay, there's your theta. He kicks it at 40 degrees. The opposing team then lets the ball hit the ground, and the punting team grounds the punt. So what happens is our punt does something kind of like this. All right? So he kicks the ball, and basically the other team doesn't catch it. It hits the ground, the other team grounds it or whatever. Now, what we're saying here then, is this final y is -1. Okay, they let the ball hit the ground. So this initial y then is 0. So the ball lands 1 meter below at an altitude from where it was kicked. Does that kind of make sense? So again, we'd like to do really a couple of the questions we did before. What was the hang time of the punt and how far did it go? So again, we always start off with the initial velocity triangle. So our VI then is 25. And we have the same angles before, so that was 40 degrees, right? In fact, we can take those two numbers right off of page 6. So this will be 19.15, and this will be 16.07. We got this by taking 25 times the cosine of 40, and 25 times the sine of 40. All right? Well, again, let's look at the hang time first. So with the type 2, we wrote then down the how far equation. We're going to do that again. All right? Now, with type 2s, our delta y then was 0. All right? But now, it's not 0. So remember, a delta means a final y minus an initial y. Right? And so that would be -1 minus 0, or the ball falls a -1 meter below where it started. Okay, let's put in everything else we know. We know the initial velocity and the y. We know what the acceleration is. Now, let's put everything really on the left side. So what we've got is 4.9 t squared minus 16.07 t minus 1 equals 0. All right? Now this is a true quadratic equation. All right? You won't be able to really factor these, so you'll probably have to use the quadratic equation here. Now there is some software. Some of you might have apps or things on your graphing calculators that can help you. And if you ask me, I'll help you with some of the software if you have that. And you can use that to kind of help you here. But regardless, really, what you need to do is use the quadratic equation. And again, this is something we learn in mathematics. Okay, do you remember this? Negative b plus or minus b squared minus 4ac, all that's in a square root over 2a. Now, you should basically kind of know how to use all this, right? So this is our A coefficient, this is our B coefficient, there's our C coefficient. So let's put our numbers in here. So we want negative B, but B is negative 16.07. So I'm going to put 16.07 plus or minus, then B squared minus 4a, a is 4.9, c is negative 1. Watch your signs. Over 2 times a. So there's your quadratic equation. Now what you have to do is just go through all the mathematics. Okay? So I'll do it in a couple steps here. So your radical, you should get what? Around 277.8449. All right. Now it looks like I've kind of run out of room here, so I'm going to kind of whoop right up there. All right. Now this is pretty challenging mathematics. You got to be real careful here. So what we're really saying here, if we do the square root here, what we're really saying is we have 16.07 plus then 16.67 all over 9.8, and then we have 16.07 minus 16.67 all over 9.8. That's your plus and minus, right? So I took the square root of this, I get 16.67. Okay, so I can add it to 16.07 divided by 9.8, then I can do the minus. So what we really get again are two solutions. So our first solution then would be time is 3.34 seconds. Our second solution then is time is negative 0.06 seconds. Again, if you work through that. So what is this really telling us here? So it's going to be at this point at 3.34 seconds. That's the hang time. All right. Now, what does this negative 0.06 mean? Well, if we had backtracked this parabola back to the ground, that would be then negative 0.06 seconds. So here, this is time 0. Backtrack it back, negative 0.06 seconds. Forward track it, 3.34 seconds. So it's asking for the hang time, 3.34 seconds. All right? Now, what about then how far does the punt go? Well, that's pretty easy, really. How far would be our delta x idea. Okay, this is the hard part. This is pretty easy here. Delta x then is our Vx times our t. So that's 19.15 times then this 3.34 seconds. And we get then a delta x, oh, what is that, around 64 meters. All right, so the punt goes about 64 meters or 64 yards, which is approximately true here. Now, how did that really compare by analyzing it as a type 2? Well, a type 2 parabola, we got a time of 3.28 seconds. Here we're getting a little bit more than that, okay, because this is a more realistic view of what the punt probably did, assuming nobody caught the punt, all right? Forward, it moves about 62.8 meters. With the type 2, type 3, it's around 64. So with that little extra time, it goes a little bit further, okay? Now let's go to the next page. That'd be page 9, right? Okay, page 9 is kind of a soccer example. And you guys probably know enough about soccer. Some of you play soccer, you know. Often you get like a free kick, and then that person there in the midfield or whatever can kick it towards the goal. And the idea is to make a goal. Sometimes the ball goes over the goal. Sometimes it hits the crossbar. You know, sometimes you get a goal, really. So this is kind of a problem about that. So this is going to be worked a little bit differently here. It says a soccer ball is kicked directly towards the goal from a point 32 meters away. So this would be our delta x idea, okay? So this guy's kicking, or this person's kicking a soccer ball from 32 meters away from the goal. Okay, so the ball then has some sort of a trajectory kind of like this, right? So the ball leaves the kicker's foot 20 meters per second. So there's your VI at an angle of 37 degrees. There's your theta. The top of the goal is 2.5 meters high. So I'm telling you that the goal is 2.5 meters tall. All right. The ball hits nothing in flight, and air resistance is negligible. Determine the time it takes for the ball to reach the goal. So we'd like to figure out the time it takes for the ball to go here to this position right here. Do you see? That's a type 3 parabola. All right, we want to get the time. Then we'd like to know, will the ball hit the crossbar? Will it sail over the goal? Or will the shot score? So we really want to know the altitude or the height, the delta y of the ball at that specific location. Does that make sense? We want to know if the ball will score or not. Okay, now this is going to work a little different than the first one. But as always, let's create our initial vector triangle. Okay, we know the VI then is 20 meters per second. We know then the angle's 37 degrees. All right, so this would be our VIX, VIY. So when we do that, this will be 20 times the sine of 37. This is going to be 20 times the cosine of 37 degrees. So our VIY, 20 sine 37, I get around 12 meters per second for that. 20 cosine 37, I get around 16 meters per second for that. All right, again, that stuff should be pretty easy for you. All right. Now, what we want to get is time. Well, before in the previous problem, you know, I told you where the ball were, the two locations of the ball, the delta y, yf minus yi. Here I don't really tell you that. We know where the ball starts, it's at the ground, but we're really not sure the height. That's what we want to find, where the ball ends. One of the things we wanted to find on the last problem was how far did the punt go? Well, now I'm telling you how far the soccer ball goes, 32. So let's actually start off this problem a little bit differently. Let's start off with our delta x equation. We know that's going to be Vx times t. All right? So we know the delta x, and we know this x velocity is 16. Do you see then we can solve this for t? 32 divided by 16 is the time, 2 seconds. Okay? So what we're saying is the ball takes 2 seconds to reach this point here. Well, now that we know what the time is, we can figure out then how high will the ball be, and we can compare it to the goal. So we can now use our how far equation vertically. All right? So our delta y then is our unknown. Our VIY is 12. Okay, 12. We'll take it times the time, 2, plus 1/2 times negative 9.8 times 2 squared. All right, again, work through the mathematics there, not too hard. We get 24 minus 19.6. We get 4.4. Okay? That's telling us the ball at the position of the goal is 4.4 meters above the ground. The ball is above the ground, 4.4 meters. So the question was, will the ball hit the crossbar? Will the ball sail over the goal? Or will the shot score? Well, the goal is 2.5 meters and the ball is 4.4. So the ball will sail over the goal. All right? In fact, if you were to subtract these two numbers, 4.4 minus 2.5, we get, what do we get there? 1.9. So at the position of the goal here, the ball is 1.9 meters above. It wasn't a goal, was it? It didn't get in the goal. It sailed over the goal. Okay? Again, that's another type of a type 3 analysis, all right? I'm going to give you a couple for practice. Now, I've got one more page on the notes. It's page 10. Now, I won't really spend a lot of time with this, but on our planet we have wind, we have atmospheric resistance. What exactly does the atmosphere do to a trajectory? Well, there's some software you can get that you can actually plot out different sort of trajectories with and without air resistance, which is also called drag. All right? Now, so this is then without air, and then this curve is then with the air resistance. You can see kind of where the wind will shorten the parabola, shorten the trajectory so the ball doesn't go as far, and it also doesn't go as high. So this air resistance really counters how far the ball goes and how high it goes. Now, you guys have probably been at soccer games that's been pretty windy. You know, generally the coach will say, you know, keep the ball on the ground or hit the feet of the player, you know, because the longer the ball's in the air, you know, the higher the trajectory, the more contribution of the air, or the more impact the air will have on the ball, you know. So you've probably been at soccer games, you see it's a very windy day and the ball goes up and it almost kind of comes back to the kicker, you know, on some of our windy days. It basically loses a big chunk of that trajectory. Okay, guys, hey, you're doing good stuff. This is pretty hard stuff. Hang in there. Hang in there. We'll talk to you later, guys. Bye.